Hello and welcome to Algebra 2 with Mr. Clausen. Today I want to talk about classifying linear systems. Specifically, I want to talk about the definitions of independent, dependent, and inconsistent systems of equations, and then finish off by going over some examples of how to classify sets of linear equations. So without further ado, let's get started here. So whenever you want to define an independent, dependent, or inconsistent system of equations, I think it's important to talk about what they look like visually. So for example, this first set of equations here, a system of equations, is just represented by a set of linear equations in this given case. So just to get us started here, I'm going to graph y equals x minus 2 and y equals negative 2x plus 7. And if you're watching this video, I would actually encourage you to pause and practice drawing these out, because that's a skill you're going to want to have. It's something we've talked about previously, but I'll also go through these so that you can check and see where you're at. So if we're going to graph y equals x minus 2, negative 2 is the y-intercept, slopes 1 to 1. This is y equals x minus 2, and y equals negative 2x plus 7. Y-intercepts at the 7. Slope is negative 2, so it's 2 down, 1 run. Alright, and with this system of equations, just by brief analysis, I can tell you that this system of equations has one solution. And this is a key characteristic of an independent system of equations. And the main characteristics that you'll see with independent systems of equations is that the slopes for each equation are different. And something to keep in mind as we're going through the rest of this exercise. And most of these sets of systems of equations that you're going to get if you're asked to solve are going to be independent, because you're looking for one specific solution. This is a very common type of example you'll observe and be the most common that you'll interact with. The second system of equations that I want to look at is y equals 3x plus 2 and y equals 3x minus 1. Again, if you're feeling a little rusty in graphing your equations, I encourage you to pause and write this down as we're going through it. So y equals 3x plus 2, y-intercepts at 2, slope is 3, so it's 3 rise to 1 run. This equation represents y is equal to 3x plus 2. And this equation represents y equals 3x minus 1. Now, a key characteristic that I'm hoping you notice with this particular set is that there are no solutions. And the main reasons for this is that the two lines are parallel to each other. If two lines are parallel to each other and there's no solutions, that means the system is inconsistent. And the main characteristic that you'll notice for these type of systems is that the slopes are equal, but the y-intercepts differ. Now with this last system of equations that I want to talk about, I'm going to graph y equals negative 4x minus 2, and then we're going to talk about the other equation here. So intercepts at negative 2, so it's negative 4 for every 1 run. All right, and here we have y is equal to negative 4x minus 2. Now, I'm just going to simplify this one a little bit, but I'm going to see that if I go 8x divided by negative 2, that gives me negative 4x. And if I take 4 and I divide that by negative 2, that gives me negative 2. And oh wait, this is the exact same thing. So this line both represents y equals negative 4x minus 2, and it also represents y is equal to 8x plus 4 all over negative 2. And so with this, we will see that both equations are the same line. And what this means is that both equations are parallel, but they are also on top of each other. And so what you'll notice with these systems, just like with inconsistent systems, that the slopes are equal and the y-intercepts. And whenever you have this type of system occur, you call it a dependent system. So some of the names that you're seeing here are given with some purpose. So for example, if you have an inconsistent or dependent system and you're looking at science fair data, for example, this actually will give you a little bit of a clue in that the independent variable that you're controlling actually does not have any effect on the dependent variable that you're trying to observe. So something to kind of keep in mind when you're looking at some of this. But with that said, we talked about these three basic systems. So now let's practice classifying some sets of linear equations. Now, you don't need to graph these every single time that you want to classify a set of linear equations. I think you can just look at it, because what I just showed you in the previous slide is that all you need to know is how the slopes relate to each other, and as long as the slopes differ, then you know you have an independent system. But if the slopes are the same, then we need to go one additional step and see how the y-intercepts match up. So if we look at this first example here, an easy way to do this is to just put everything in y equals mx plus b format. And the only reason I say that is I look at these guys and I feel like, ooh, like they're similar, but like it just seems like signs are switching back and forth. And so an easy way to do that is to just put everything in y equals mx plus b format. It's really hard to mess up if you do that. So I'm just going to put y in the positive way on one side, and this will give me y equals 7x minus 6. And if I do the same thing here, I go and I add 7x to both sides just to get a positive y all by itself. What you'll notice here is that I have slopes that are equal. And if I have slopes that are equal, that tells me that this is either a dependent or inconsistent system. So it gives me two options to look at here: inconsistent and dependent. Now, the other piece of information here is that the y-intercepts are also the same. And what this will tell me is that this particular system is a dependent system based on this breakdown. And so we can classify this really quickly if you put everything into y equals mx plus b format. Now this one, I can do a little bit of manipulation here. I could leave it in standard form if I wanted. Let's divide everything by 4 just to see how all this crashes out. And I could see that this would give me x plus 2y equals 3 and x plus 2y equals negative 3. And I can tell you right now that this is a inconsistent system. Everything with the y and x terms are equal. I know their slopes are going to be the same, but the y-intercept's going to be a little bit different here. And so I can just rearrange it so that you can see it. That would be one of the equations, and this would be the other equation. So that's the difference that you're looking at if you were to arrange these in y equals mx plus b. But I could just stop here and say, hey, I can tell you, based on some analysis, that the slopes are going to be equal. But the y-intercepts are different. And so just like our previous example, we wouldn't circle dependent. We would actually identify this as a inconsistent system. And something you can derive out really quickly. Now this last example, I'm going to take a little bit of a look at it. I can see some things are kind of flipped around here, and it might be easy enough to tell just by analyzing that this is an independent system. But, you know, if you're having a hard time seeing it, just put it in y equals mx plus b format. So you can go and add 2x to both sides here. This would give you 4y is equal to 2x plus 6. Move this around. Actually, you don't need to move that around at all. This will give us y is equal to 3 over 4x minus 3 over 2. And if we divide all that by 4, by 4, by 4, get y is equal to x over 2 plus 3 over 2. In here, it doesn't even matter what the y-intercepts are in this particular case. I see right here that the slopes are different, and therefore the system is independent. And it doesn't even matter what else is going on. If the slopes are different, you know that it is an independent system, and that this equation, for example, would have one solution. The inconsistent system would have no solutions, and the dependent system would have infinite solutions. And so these classifications give you a really quick breakdown of the look and overall behavior that exists within them. So with that said, I hope this video gave you a really brief breakdown of how to identify independent, dependent, and inconsistent systems, and gave you some tricks in how to identify these really quickly without even the need to graphing them. So with that said, I'm going to leave you to it, and let's do some math.